So hi guys, welcome back to our channel Code with AP or welcome to our channel Code with AP. This video is all about caching. I've explained all the caching strategies, cache hit, miss, ratio, all the eviction policies, invalidation, placement patterns, distributed caching. I've talked in depth about what is Redis and why do we need it. So this video will cover all about caching you need to know for the interviews. And without further ado, let's jump into the video.
So hi guys, welcome back to the channel. So this video is all you need to know about caching. So if you ever been asked how you design a system that handles million requests per second in an interview and you just have answered like can we add just Redis, this video is for you because that answer is somewhat incomplete. Most developers know that caching exists, they know Redis exists, but when the interviewer says okay, which caching strategy would you choose and why, that's where people kind of freeze. So today this is going to fix that. This video is for that. We are going to cover everything from the absolute basics of what a cache is, all the way to the Redis internals, the eviction policies, consistent hashing, cache stampede, then some interview questions at the end. So whether you are preparing for an interview or building systems, just stick around. This video will give you a lot. This video will change your thinking about caching. So let's go. So I've divided the video into 8 sections. We have 8 sections today, and we'll start with the fundamentals and go progressively deeper. The last section is a full interview questions thing, so if you want, bookmark that timestamp right now. So without wasting any time, we'll begin with the video. Alright, let's start with the fundamentals. So firstly, we'll discuss what is a cache. So cache is a fast temporary storage layer that holds copies of frequently accessed data. The idea is simple. Instead of going to your slow database query every single time, you store the results in a fast place and serve it from there. Now look at this flow. A client request comes in, it hits the cache first. If the data is there, great, you are done in microseconds. If not, it falls to your application server, which goes to the database, gets the data, and you optionally store in the cache for next time. Okay, now how much fast are we talking? A database read might take 5 to 15 milliseconds. A Redis cache hit under a millisecond. We are talking 100x faster. And here's the really important number. In a well-designed system, 80% or more of all read requests should be served directly from the cache. This means 80% of the load never even touches your database. Obviously, it touches for once. That's why every company at scale uses caching. Alright, let's get clear with some terminologies because these will come up later in the video also and in your interviews also. So firstly, it is the cache hit. Now the cache hit is the requested data is found in the cache, served instantly. Like there was no need to go to the database and curate, it was found in the cache. Beautiful. Now comes the cache miss. Now the data is not found in the cache. You go to the database layer, slower. Then you typically store the result in the cache. So in this, you need to hit the database. Now third comes the hit ratio. Now this is important. This is the key metric. It's simply hit divided by the total request. In production, you want it around 80 to 95%, and if it is 50%, something is going wrong with your caching layer. Now here's something most developers, or you can say junior developers, don't know: the cache stampede, also known as the thundering herd problem. So imagine a popular cache entry expires at that exact moment. 10,000 concurrent requests all get a cache miss. They all go to the database at the same time. Your database will collapse if it is not acquired for that. So this is a real production incident waiting to happen. We'll talk about solutions like mutex locks and cache miss and probabilistics early expiry when we get to the cache invalidation part later in the video. So yeah, the point that you need to remember is whenever you are designing any system in an interview, always mention what your hit ratio is. Okay, so now let's start with the cache eviction policies. So, what are cache eviction policies? These are algorithms that determine which data to remove from a full cache to make space for new relevant data, maintaining system performance. So basically, the best policy depends on workload, such as using LRU for general scenarios or MRU for cyclic data. We'll discuss them one by one. Now, whenever your cache is full, something has to go from it. So the eviction policy decides that. Now let's go through them one by one. First is the least recently used. This is the most common one. You evict the item that hasn't been accessed for the longest time. The intuition is if you haven't needed it recently, you probably won't need it soon. Okay, now LRU is the default go-to. Redis supports it. Memcached uses it. We'll discuss them later in the video. If someone asks you what eviction policy do you use, LRU is a safe answer for most use cases in the interviews. Second comes the LFU, frequently used. So instead of recency, this looks at frequency. You evict the item that's been accessed the fewest times overall. It is great for workloads where certain items are always hot. Now, this is frequently asked in interviews, especially the follow up. When would you use LFU over LRU? Now, the answer would be whenever your access pattern is frequency skewed, like a music streaming app where top 10 songs get 90% of the plays, there LFU would be a better choice over LRU. Next comes the third important one is the FIFO, first in, first out. Now, in this, we evict out the oldest item by insertion time, regardless of how often it's been used. It's simple, but actually usually not great in practice. Okay, now fourth is the time to live, TTL. Every item has an expiry time. Whenever it expires, it's gone simply. This isn't strictly an eviction policy, like we can't classify it, but yes, it works alongside others, but it's used everywhere. Every Redis key should have a TTL unless there's a very good reason not to. You would always have a TTL. Now comes the random replacement. It's just called random also. So just pick a random item to evict. Like sounds stupid, right? But research shows that for many workloads, random eviction performs surprisingly close to LRU. It's used in CPU caches because it's so cheap to implement. Now, this one ARC adaptive replacement cache, this is the advanced one. ARC maintains two LRU lists, one for the recently used item and one for the frequently used item. So you're getting a hint that it is a combination of first two, and dynamically adjust the balance based on the actual workload. It's used in ZFS or IBM based storage system. Like if you mention ARC in an interview, you'll stand out because many people wouldn't have heard of it, but it has to be of a specific use case. Remember that. Last one is the sieve. It's basically a modern high performance algorithm that uses lazy promotion and quick demotion to improve upon LRU for web workloads. Like it often reduces missing ratios. Now let's discuss the right strategies on cache. So basically, when you write data to your database, what happens to the cache? So there are three strategies for it. Now, the cache write strategies determine how data is updated in both the cache and the underlying database. And there are three main strategies: a write through, a write behind. It is also known as write back. And the third one is the write around. Now let's discuss one by one. The first one is the write through. So in this strategy, every write goes to the cache and the database synchronously. The write only completes when both succeed. The pros is that the cache is always in sync and there is no risk of stale data and there is no data loss. And the cons includes that every write is slower because you wait for both the cache write and the DB write. So basically we use this when we need strong consistency, financial transactions or inventory updates. Anything where stale data is dangerous, we can go with the write through strategy. Now the second one is the write behind, which is also known as the write back. So you write to the cache first, then the cache acknowledgement comes back immediately, and then asynchronously the data is flushed to the database in the background. The pros is that it is blazing fast writes from the client's perspective, and there is a huge reduction in the database from the write load. And the cons includes that if your cache server crash before flushing to DB, then you lose data. This is eventual consistency, and you have to figure out which one you have to use. But you use this one when you can tolerate some data loss, like analytics counters, click tracking, log aggregation, things that can be slightly approximate. Then the right behind strategy is the best one for there. The third one is the write around. So the writes go directly to the database, bypassing the cache entirely. The cache is only populated on reads, basically when the cache misses it. Now the pros includes that prevention cache pollution, and it is good when data is written once and rarely read. It prevents cache pollution. Then the cons includes that the first read after a write will always be a cache miss, and we use this when you are writing large data sets that won't be reread soon, log files like archive data. Now let's begin with cache invalidation. Now this is going to be the hardest part of caching. This is a famous quote by Phil Carden that there are only two hard things in computer science: cache invalidation and naming things. This is a joke, but it's also completely true. Cache invalidation is genuinely hard. Now the problem is that your database has been updated. The cache still has the old data. So now how do you make sure that the cache reflects reality? Now there are four strategies to it, of which I've written all the four in a slide. So we'll go on them one by one. Now the first one is the TTL expiry. Now this one is the simplest approach. You just set a TTL on every cached item. When it expires, the next request fetches fresh data from the database. Now this is simple and reliable, but what happens is that your cache may serve stale data right up until expiry. And for a user's profile data, maybe that's okay, but for stock prices, it is definitely not okay. The second one is the event-driven invalidation. This happens when the database is updated, you fire an event, and a listener invalidates the corresponding cache key. Here we take care of the real-time consistency. It is more complex to implement, but it gives you the true freshness, often done with a message queue like Kafka or RabbitMQ. The strategy 3, we can term it as cache aside with explicit delete. Now this one is very common and very commonly used basically. When your app writes to the database, it also deletes the corresponding key from the cache. This is good. The next read is a mess, fetches fresh data, and it repopulates the cache again. This is simple, clean, and effective. Strategy 4 is also there, which is the versioned keys. Now instead of invalidating keys, you version them. User profile changes and your keys goes from user 123 v1 to user 123 v2. Changes from v1 to v2. Old versions are never accessed again and expire naturally. This one is elegant, but it uses more memory. Now basically here's an important thing which you need to remember. For payment systems and inventory management, TTL alone is not enough. You must use event-driven invalidation or explicit cache deletes on write. Stale data in these domains causes real financial damage, and it can harm your application too. Now let's discuss the cache placement patterns. Now in this, we are going to discuss where and how the cache sits in your system architecture. There are four main things we are going to walk upon. Firstly is the cache aside, which is also termed as lazy loading. Now this is the most common pattern. Here's how it works. Basically, first application checks the cache first. If it's a hit, it returns the data, and if it's a miss, it's fetched from the database. Then it stores in the cache, and then it returns the data. Now this is the most common pattern. This app is responsible for all cache interactions, and the cache is basically invisible to the database. This is what most people mean when they say, okay, we cache with Redis. 95% of web applications use this pattern, which is the cache aside. And this is your go-to pattern in any interview you're talking about caching. Second one is the read through. This is similar to cache aside, but the cache handles the DB fetch automatically. The application only ever talks to the cache. On a miss, the cache library fetches from the database itself. It's cleaner from the application's perspective, but it has less boilerplate code also. Now let's move on to the third one, which is the write through. Write through, this we have discussed previously also, but as a placement pattern, every write goes through the cache to the database. Cache is always up to date, and we have covered the trade-offs earlier. Now, the last one is the refresh ahead. This is the most, we can say, sophisticated pattern. The cache proactively refreshes items that are about to expire before they actually expire. So your hot data is always warm in the cache. No users ever experiences a cold miss on popular data. So that's why before expiration, it asynchronously refreshes data in the cache. This is used at scale. Think Netflix, movies, metadata, Twitter's trending topics. On that, we can use this. Let's discuss about distributed caching. This is the ninth section. Everything we have talked about so far works great for a single cache server. But what happens when you need to scale up? On Redis, no, one Redis node can do a lot, but at a certain scale, it becomes a disaster. So, in for the solution, we have consistent hashing, which we will discuss just now. Now, this is a key concept. Now, firstly, we'll discuss the problem. If you have 4 cache nodes and a new request comes in, which nodes holds the data for, let's say, user 1, 2, 3, to which node the request goes. Now, the naive approach was this. We do hash of that key mod, total number of nodes we have, simple. But if you add a 5th node, now almost every key maps to a different node. You have just invalidated your entire cache, and that's a disaster. Now, to solve this, we have something as consistent hashing. Now, this would require a totally different video, but we'll discuss it in brief over here. Consistent hashing solves this. Keys and nodes are mapped to positions on a virtual ring. A key belongs to the nearest node clockwise from its position. Now, when you add or remove a node, only the keys that map to that specific arc on the ring gets remapped. Everything else stays put. This is how we ensure that there would be minimal disruption. Now, this is why Redis cluster uses a variant of consistent hashing with hash slots. They call it as hash slots. Now, Redis specifically uses somewhat 16,000 hash slots distributed across cluster nodes, and this gives you smooth horizontal scaling too. Now, this would be the 10th section. Let's discuss about popular caching tools and technologies that are available for us, and what should we actually use. So, first, obviously, if you are watching this video, you would be knowing about Redis. Now, this is the default choice for 90% of the use cases. Now, let's discuss the reasons behind it. It's incredibly fast. It has sub-millisecond latency. It supports a rich data structures such as string, hashes, lists, sets, sorted sets, bitmaps. Geospatial data is now also supported. It has built-in TTL, pub/sub models, and Lua scripting is also there. Persistent options, and it has cluster support for horizontal scaling. We use Redis for session caches, leaderboards, rate limiting, real-time analytics, pub/sub models, distributed logs, and whatnot. Redis has all the reasons to be the most used tool for caching. Second comes the memcached. This was simpler, and it is multi-threaded. Now, you can study about multi-threaded, or like make a video on this. Great if you just need fast string key. value caching and nothing fancy, like no persistent, no replication, no complex data structures is there. It still uses it is still used at Facebook at massive scale. The multi-threading makes it better than Redis at a raw CPU utilization on modern multi-core machines. But like Redis has mostly won this battle for new systems. Now, this one is a CDN cache, third one. This includes like Cloudflare, Fastly, AWS CloudFront. Now, this is edge caching. Your data lives on servers physically close to your users, and it is distributed globally. You use HTTP cache headers like cache control, e tag, last modified to tell the CDNs of how long to cache your responses. And it is critical for static assets, JavaScript bundles, images, HTML pages, and some like public API responses too. The last is one is the local in process cache. It is also referred to as the L1 cache, like this. L1 cache. Yeah, right. Sometimes the fastest cache is the one inside your own application. So like the Java developers use a caffeine or a guava cache, and Python has I think functools.lru cache, somewhat like that, and it has zero network latency, but only works for single node deployments. If you have multiple app servers, each has its own cache, and they can get out of sync. It is super useful for config values, small lookup tables, and computed values that don't change often. Okay, so we have talked about Redis earlier. Now let's discuss why is Redis so fast. So when you ask this to someone, most people would say that because it is an in-memory database. It is true, but like it is somewhat incomplete. We'll go into the depths. Now, the first point is that it is a single-threaded I/O. Basically, Redis processes commands in a single thread. There are no mutex locks or no thread contention, which you would have studied in operating systems, and there are no race conditions. But like then how it handles thousands of concurrent connections? The answer is I/O multiplexing. Redis uses this a pole on Linux and a KQ on Mac OS to handle thousands of socket connections with a single thread, and it only processes each one when it's ready. Now this gives it a predictable and ultra low latency, and every command completes in microseconds. Second part is that it is has optimized internal data structures. Redis doesn't uses generic structures. For small sets, it uses a zip list. It is a compact byte array, and for larger set, it switches to a hash table or skip list. It automatically upgrades between representations as your data grows. So it is zip list, and second one is the skip list. This is why Redis uses far less memory than you would accept for typical workloads. The third point is the persistent. But wait, if Redis is in memory, what happens when the server crashes? Does it crash also? So here is a concept of RDB snapshots. Redis periodically forks the process and writes a point in time snapshot to disk. It is fast to restore, but you lose data since the last snapshot. And the second is AOF, which is termed as append only file. In this, every write command is logged to a file, and on restart, Redis replays the log, and slower to restore, but it has minimal data loss. So the production recommendation here would be that we use both RDB for fast restores and AOF for minimal data loss. Now the second last is Redis cluster. It has hash slots. We have talked about it also in the earlier video. Now, as I mentioned, Redis cluster uses 16,384 hash slots. And the method to find which slot is this CRC16. This is the key mod, the total number of hash slots. The cluster maps slot ranges to nodes, and this gives us automatic data distribution, the failover, horizontal read scaling, the replicas which we have discussed. The last one is that it has the pub sub and the streams, which you would have obviously heard about. It has built-in pub sub messaging, and it uses Redis streams like Kafka Lite for durable and long-based message queues.
Okay, so for now we have discussed all the strategies. Now let's go on to when to use which one. This will be our second last section of the video. Now I've brought it all together. This is a quick reference for the most common scenarios you would fall into when building a system. So firstly is a read heavy API. This is the classic and most common thing or the scenario you would go. Uh, let's say you have a product catalog. In that, the strategy which you will go is cache aside, you will have the LRU eviction and a TTL, time to live. This is a classic one. The tool which you would use is Redis. Second, you would use an user session management. You would use a write through strategy over here because you always want to persist sessions and a time to live Redis. Third one is a real-time leaderboard when you are building a leaderboard. So there you can have Redis sorted sets. Now this is literally what sorted sets are made for, a leaderboard. So it is very helpful over there. These are the internals of Redis, so you should know about them. Fourth is rate limiting. Redis is extensively used in there. There is a concept of Redis INCR plus expire, uh, and you would use auto atomic increment and TTL. This is very fast and elegant. The third last is static assets and web page. So there is obviously CDN caching. We don't use Redis for this. We use Cloudflare or CloudFront. Now, the second last one is high throughput analytics or the counters. There you use right behind. This is a very specific use case. You don't need real-time DB consistency for analytics, obviously. So you write fast and you flush to DB in batches. You can go behind the video and see what a write behind was. And the last one is when you have microservices with distributed state. In there, you use cache aside and Redis cluster, and you do consistent hashing. We have also discussed consistent hashing, and I would make a different video also on this because this is a very important concept. Now, this will be the last section of our video. We will discuss some common interview questions, the most asked ones in system design interviews or any interview in which you would bring up caching. Now, first question can be what eviction policy does Redis use by default? You can think of an answer, obviously. So the answer for this is no eviction. That means it returns an error when the cache is full, and then you must configure LRU or LFU explicitly. More importantly, that you should never leave eviction policy as no eviction in production. You should set it to all keys LRU this time. All keys LRU for a general cache. The second question, the second question that can come up is it can ask a difference between write through and the write behind. So write through is synchronous. Data is written to cache and DB in the same request. It has strong consistency, higher latency, and a write behind, whereas it is in asynchronous, and you write to cache first, then it flushes to DB later. It has higher performance, but it has a risk of data loss, obviously, because you write to cache first. There is a trade-off in them, which is of consistency and performance, which you have to make according to your system. The third question that can come up is how do you handle cache stampede? In there, you have basically three options only. Firstly, is the mutex lock. Only one thread fetches the DB data on the mess, and the others are waiting. So you have just logged the others, and only one is performing all the tasks. Second is probabilistic early expiry. What is this? is basically it is you start refreshing before the TTL time to live hits zero. And the third one is a background refresh. In this, you proactively refresh hotkeys before they expire. And you mention at least one option in an interview, and you can obviously say all three to impress the interviewer. Now, let's move on to the fourth question. It can be of consistent hashing and regular hashing. These are very important. Regular hashing, as you would know till now, it is this formula, key mod n, uh, is used in regular hashing, and adding one node remaps almost all keys. And that is where consistent hashing comes. In this, the keys are mapped to a ring, which we discussed earlier, and adding one node remaps only how much keys? It is 1 by n, and not all the keys. This is why consistent hashing is essential for distributed caches. Now, the last question. Uh, this is a very good question. When would you not cache something? In here, there are four things which you can remember. Basically, the data that changes too frequently. You do not need to cache that, obviously. Cache would always be stale uh, because the cache would not be updated because the data is changing frequently. Second is the security sensitive data like passwords, private keys. You never ever cache them. Third is the very small data sets that are already fast. So there is no need to get a overload of caching, introducing Redis over there. And the fourth one is that data that needs asset consistency guarantee. There also you do not need Redis. Okay, so that's it for the video. You all now have a more complete understanding of caching than the vast majority of developers. Now let me leave you with five key takeaways. First is the always remember the least recently used and time to live. It covers 80% of the use cases. Second, remember cache aside. Third, always remember a write through. Fourth is consistent hashing. And fifth, always monitor the hit ratio. If it drops below 80%, something is going wrong. Now, if this video helped you, please like and subscribe, and it genuinely helps me keep making content like this. You can drop a comment on what system design topic should I cover next, or what topics would you like to hear, like message queues, load balancers, many more things we can plan up upon. Resources I've attached, some resources I've attached in the description, and if you all would say, I would also give the notes of my. Okay, so this is all about the video. I'll see you in the next one. Bye bye, guys.